All right, guys, you are welcome to the GMAT 41's YouTube channel. In this live stream section, we are going to look at part 1 of the periodic table. Part 1 of the periodic table. In this part 1 of the periodic table, we'll give attention to the following things showing on the screen, as you can see. All right, so we're going to look at the periodicity and modern periodic law. We'll give attention to groups and period. In the periodic table, we have what we call the groups. We have what we call the period. What are these? Then we are also going to look at electronic configuration and block of elements. That's the block that an element belongs to. All right. Then we are going to consider the electronic configuration and then the group and period of an element. What is the relationship between the electronic configuration and the group that an element belongs to, as well as the period? Then, conclusively, we'll look at families and names of the groups of the periodic table. So this is going to cover part 1 of periodic table. So, you're welcome to today's lesson. As we move on into these tutorials, we are going to first give attention to what periodicity is all about. When you hear periodicity of an element in the periodic table, right, what do we actually mean? Now, I want to quickly take your mind to the aspect of periodic motion. This is about something reoccurring. It's about something reoccurring, okay? And so the idea of periodicity simply tells us that in the periodic table, there are certain properties that reoccur at certain interval. That property will reoccur. Now I'm going to quickly give you an example. Maybe if you talk about a particular group, there is something that is peculiar to that group. One of it is the fact that every member of a group has the same number of electrons in their outermost shell. So this is something that repeats itself at regular interval. All right, and that is the idea of periodicity. If you move to a particular period, you would notice a trend also. Now, if you come to a particular period, all the elements in that period, they are going to have the same number of shells. So you've gotten the idea of what periodicity is all about. It's simply the recurrence or repetition of certain properties in the periodic table. All right, let us talk about the modern periodic law. Modern periodic law. So to start with, I would like us to get a little background of this periodic table, okay? Yeah, because the law is based on that periodic table. I think one of the most widely used concepts of the periodic table is that proposed by Mendeleev. Although in the modern periodic table, that table proposed by Mendeleev has been modified, and that is the one that we actually make use of now and we deal with in terms of the periodic law. Okay, and that modern periodic law is actually proposed by Henry Moseley, I think in 1913. That's 1913. All right, by Henry Moseley. So that modern periodic law, what does it state? I hope you're with your writing materials, and so you can put down what I'm about to state. So the modern periodic law states that the properties of elements in the periodic table is a periodic function of their atomic number. So simply put, properties of elements in the periodic table is a function of their atomic number. So when you talk about the physical, the chemical property of elements in the periodic table, we actually base it on the atomic number of elements. So that is why the concept of atomic number is very important. And I hope you already know about the atomic numbers of elements. It's obtained from the serial numbers of the arrangement of this element. For example, if we talk about the first 20 elements, starting with hydrogen, helium, lithium, beryllium, boron, carbon, that arrangement, okay? Yeah, then up to calcium, number 20. That arrangement is the same as the atomic numbers. All right. So having stated the modern periodic law, remember what I told you, this modern periodic law that we make use of now is proposed by Henry Moseley, not Mendeleev. Henry Moseley modified that of Mendeleev that have long time actually been used, because that was the particular proposition that gave room for other amendment. So the modern periodic law was proposed by Henry Moseley. All right, now let us talk about the periodic table. What is the periodic table? What is it? I want to talk about it. Okay, the periodic table. Showing on the screen, you can see what the table looks like. Now I've decided to show the periodic table for the first 20 elements. Now the periodic table is simply a table that shows the arrangement of elements in rows and in columns. I'm sorry that the one of group 3 and 4, that line is missing. Okay, is missing, but I think I can still show you something. All right, let's look at this. Good. So this is the periodic table. So it's simply a table that shows the arrangement of elements in rows and in columns. Take note of that. You can put it down. Periodic table, a table that shows arrangement of elements in rows and in what? In columns. Which means that if we talk about the periodic table, we have, the parts that we refer to as the rows, and we have that which we refer to as the columns. Now, simply put, the rows are the horizontal arrangement. The horizontal arrangement, moving from left to right. That forms the rows. And that rows are called periods. They are called what? Periods. So imagine that you are asked to define periods, or which of the following defines period. The period of the periodic table is simply the horizontal arrangement or the row arrangement of elements in the periodic table. I repeat that. The arrangement of elements in rows horizontally in the periodic table. That is what we call the period of an element. And it is very important for us to take note of this, because there are certain information that the period of an element gives to us with regards to that element. Now, looking at the periodic table showing on the screen, you would notice the numberings that I use black pen. Those numbering that I use black pen for. So moving from left to right, are you getting? Moving from left to right, we have period 1, we have period 2, we have period 3, we have period 4. Please, this lesson will be based on the first 20 elements in terms of this periodic table. In part 2, where I will go further to explain in depth the concept of the lanthanide and the actinide. Good. You're going to see the modern periodic table in full, right? That has 18 groups. See, this one, we just limited it to 8 groups, okay? Now let us talk about the group of an element in the periodic table. The groups of an element in the periodic table. That is where we talk about the vertical arrangement, the columns. Is that okay? Now showing on the screen, you can see those numbers I use red pen to show. Okay? Now this number that I use red pen to write, moving from up down, okay? Moving from what? Up down, up down. So that column arrangement, that vertical arrangement is what we refer to as the group of the elements in the periodic table. So how do we define the group of an element in a periodic table? It is simply the vertical arrangement of elements in columns. Group of the periodic table is simply the vertical arrangement of elements in the what? Periodic table. So I hope you get that concept. And for this, our first 20 elements analysis, okay, we have 8 groups, starting from group 1, you see group 2, group 3, group 4, down to group 8 or 0. All right, so I hope that you are following up with the explanation being given. So this is much like the look of the periodic table for the first 20 elements. So you can see that here we have 8 groups and 4 periods. But before our part 2 class, in the next video lesson where we treat chemistry, I want to tell you that in the modern periodic table altogether we have 18 groups and 7 periods, okay? That is the one that will also show us the series that we call the lanthanide series and the actinide series. We'd also look at the D block element, that's the transition element, okay? We're going to see that in our next class. All right, now we've looked at the concept of periodicity and of course the periodic table. We are going to move on to something else, okay? We're going to discuss the concept of electronic configurations and the group, okay, the block of an element. Electronic configuration and the block of an element. That's point 2. Now, when you hear of electronic configuration, what do we mean? Electronic configuration. You can put that down. Electronic configuration is defined as the number of electrons in each shell of an atom. The number of electrons in each shell of an atom. That is what electronic configuration is. Now, someone would want to also give attention to the relationship between electronic configuration and the block that an element belongs to in the periodic table. Because our elements are generally classified into 4 blocks in the periodic table. In our next class, you're going to see in our modern periodic table showing that 18 groups and 7 periods, you see the various sections of the 4 blocks of elements in the periodic table. But of course, that is linked to the concept of our subshells. Subshells that are obtained from their azimuthal quantum number. I made a kind of reference to it in our previous chemistry class where I actually answered some exam focus questions. Okay, the azimuthal quantum number, when you work on it, it gives us information about the subshell of an electron, okay? And then we have the S, the P, the D, and the F subshells, which also have their orbitals. So in the periodic table, elements are classified into S block, into P block, into D and F block. So you want to take note of that. It is either an element belongs to the S block, or an element belongs to the P block, or it belongs to the D block, or it belongs to the F block. Now for our first 20 elements, those elements belong to either S block or P block. Okay, those first 20 elements, they are either S block or P block. Now, it's important for you to know how we actually identify the block that an element belongs to. If I give you a particular element, say maybe calcium now, how would you know the block that calcium belongs to? If I give you something like, let's say, uh, aluminium, how would you know the class that it belongs to? So we're going to find out how to identify that. And I hope you're ready to put down the next important point. The block of an element. The block of an element is identified based on the subshell that the last electron of that element enters. I repeat, the subshell that the last electron of that element enters. So if you know the subshell that contains the last electron of an element, that subshell will now tell you the block that the element belongs to. Now, how would you know the subshell that the last electron enters? That is where the electronic configuration comes in. Because from the electronic configuration, we can find out that yes, the last electron of this element entered this subshell. And so from there, we can now say that the element belongs to so-so block. So that is one of the most general and direct approach to determining the block of an element. And of course, that's the reason why we are considering electronic configuration and block of element. Remember, I mentioned I will have 4 blocks, the S, P, D, and F block. I hope you're following, right? So at this point, we are going to look at some examples. All right? And as we look at this example, we'll find out the block that the element belongs to. Let us consider sodium. What is the electronic configuration of sodium? Sodium is atomic number 11. So please watch, let's see the electronic configuration. Good. So you see that the electronic configuration of sodium with 11 electrons is 1s2, 2s2, 2p6, 3s2, or 3s1 rather, 3s1. Meanwhile, I want to believe that you are aware of how this came up already using of Bohr's building block principle. From of Bohr's building block principle, we get to know the way these subshells and its orbital are being arranged. So you have 1s, 2s, 2p, 3s, 3p, 4s. When you get to 4s, please break, because the arrangement will now change somehow. We now have 3d. After that 3d, it will follow with ps again. So you have something like 3d, 4p, 5s, 4d, in that order. So actually refer to it as maybe once you hit your first D, you have DPS, another DPS again, then F, 4F will be welcomed. Okay, let me see if I can show you what I'm talking about in this case. Let's see what we've got here. Okay, and now the of Bohr's principle. You know, on the GMAETS 41's platform, you've got all these, you know, tutorial notes and video lessons. You get access to them when you become a member of GMAETS 41. Either you join us fully to attend our physical classes as well to in Unizik campus if you're a Unizik student, or you join us online, as the case might be, by becoming a channel member. All right, you get access to these materials. So this is the of Bohr's building block principle. You can see certain things drawn on the right hand side with arrows showing. That arrow tells us the direction in which electrons enter. Okay, from the lowest energy level to the higher energy level. So bringing out all this, you could see the arrangement. You're expected to know this arrangement and memorize it. On the left hand side, you have order of entry of electrons into the subshells. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 6f, 7d, and 7f. All right, so that's just the idea. If you take the video lesson on this, you would hear where I gave a trick to guide you. Once you hit your 3D, the movement will now be DPS. That DPS will still repeat again before 4F will come. Once 4F comes in, you have 4 DPS. That is, you have FDPS, you have another FDP, because S will terminate after that, something like that. I believe this is not much for you to memorize so as to know how this is being arranged. Okay, so let us go back. We are talking about the electronic configuration of sodium. We are talking about the electronic of sodium, and you saw it as 1s, 2s, 2p. Of course, it's moved on in that way. So let's see once again. All right, so that's the electronic configuration. So the question will now be, which block does sodium belong to? Which block of the periodic table does sodium belong to? So all you have to do is to look at the subshell that the last electron entered. The subshell that the last electron entered. And you can see that the last electron entered S orbital. That's the subshell there. You can see that 3s1. I underlined it for you to see clearly there. So that is the last subshell. Are you following, right? And you notice that that subshell is S. And that is where the last electron 1 entered. Does that make sense? Now look at the number attached to that S raised to that power 1. That power 1 you have there is, the number of electrons. So you have 1s power 2, 2s power 2, 2p power 6, 3s power 1. All those powers simply are the number of electrons. Are you following, right? Now calm down. Let us look at something here now. The numbers attached to those S and P you have there, which number is the highest number there? Now quickly, if you look at the one I underlined, you will see that it is 3. That numbers attached to the subshell, 1, 2, 2, and 3. Those numbers are called principal quantum numbers. So the highest principal quantum number there is 3. Therefore, the subshell it bears there, which is S, will now be our interest. We'll now ask ourselves, the last electron entered there, is that not so? Enter that S block of that 3s. So since the last electron entered that S subshell, it simply means that sodium belongs to the S block of the periodic table. So that is it. Now let us look at another one. Let's consider iron. Iron is atomic, chlorine first. Let's consider chlorine first. Chlorine is atomic number 17. That's the electronic configuration. 1s2, 2s2, 3p6, 3s2, 3p5. Now you notice that I underlined something, although what I underlined there, we have 3s2 and 3p5. Good. Now there is a reason I underlined it too. We are still coming to that in the next point, where we talk about electronic configuration and the valence electrons of an element, which also goes to give us the group that the element belongs to. Now, what we have to do is to look at the highest principal quantum number here and the last subshell. The highest principal quantum number in the electronic configuration of chlorine is 3, as you can see there. The last subshell there is P. So that is where the last electron of chlorine entered, that 3p5, subshell P. So since the last electron of chlorine entered that P subshell or orbital, as the case might be there. Are you following, right? We conclude that chlorine is a P block element. Chlorine is a P block element. Take note, we'll still come back to the idea of my underlining these stuffs actually. Are you getting me, right? I think the next point we are going to discuss. This Z you saw in bracket there, or you're seeing rather in bracket there, simply tells us atomic number, okay? So take note of that. It's a kind of standard used in representing atomic number. Now let us consider iron and see. Let's consider iron. Iron is atomic number 26. That's the electronic configuration there. So quickly, what you have to do is to look at, you would notice that after 4s, you go to 3d. Because if you are filling the electrons into the orbital of ion, just like I showed you of Bohr's principle, the arrangement of the principal quantum numbers, 1s, 2s, this, 2p, 3s, 3p, 4s. After 4s, that is when you start filling 3d. So the idea is you fill 4s first before moving to 3d. Okay, which means that 3d is a kind of higher in energy level than 4s. Yeah, from that arrangement, although there are still other chemistry stuff that one would have to talk about for clarity, in some cases, but for now we are not going into that area. In terms of Bohr's principle, 3d is at higher energy level than 4s, even if the principal quantum number of 3 is less. Are you getting me right? I showed you that arrangement already. So we conclude that the last electron of ion entered d block, d subshell there rather, entered d subshell, d orbital. Therefore, ion is a d block element. Ion is a d block element. Then let us consider the next one. We're going to look at this element. This is radon, atomic number 86. Atomic number 86. Yeah, there is a kind of an ordering here or something you want to take note of. Radon, as you can see there, the last electron entered 6p if you are arranging. 6p if you are arranging. You can see that, right? So it simply tells us that radon is actually a p block element, although it has f orbital in it anyway. But the last electron entered p. That's what we are seeing here. The last electron entered p, so classify it as a p block. Although when you start moving higher, there are certain things that begins to change a little, with respect to explaining all this. But anyway, for now, I believe you have the idea of what the block of an element is all about. That's good. Now we are going to look at the next item, electronic configuration and group/period of an element. How can you use the knowledge of electronic configuration to tell the group that an element belongs to and the period that an element belongs to? That is what we now want to consider. Electronic configuration and group/period of an element. We're going to be fast about it. Okay. Now there is this relationship between electronic configuration and the group or period of an element. Okay. Using this SPDF electronic configuration, the group of an element can be determined from those subshell configurations. The period is not a problem. I guess I'm going to talk about the period quickly before we move back to the group. All right. You can put this down. The period of an element determines the number of shells that element will have. The period of an element determines the number of what? Shells that the element will have. Are you following right? So if I tell you that an element is in period 2, it means that element has 2 shells. If I say that the element is in period 5, it means it has 5 shells. If I say it is in period 3, it means it has 3 shells. So you see that we can determine the number of shells of an element from its period. We can also determine the period from the number of shells. Now, using our electronic configuration, how can we now answer any question whereby maybe an examiner requests that we tell the period of a given element? Let us go back once again to the electronic configuration of sodium and the others that we've considered so far. Let's look at them further, okay? Now, this is sodium, and this is the electronic configuration, okay? Now, these numbers like coefficients attached to this SP that you see, they're not the powers, so not the powers. Like this one, you have 1s, you have 2s, you have 2p, you have 3s. Those numbers are called principal quantum numbers. I talked about that earlier. And from the knowledge of quantum numbers, principal quantum numbers simply gives us information about the energy level that an element belongs to, or an electron rather, is found, the energy level. It tells us also the shell, yeah, not subshell. It gives us information about the shell that an electron belongs to. Okay, so this idea can be used to determine the period of an element, and it is that simple. It's very simple. All you have to do is to check what is the highest principal quantum number. I repeat, what is the highest principal quantum number in the given electronic configuration. In the case of sodium, the highest principal quantum number, as you can see there, is 3, which is that one of 3s1. So since the highest principal quantum number there is 3, it simply means that sodium has 3 shells. It simply means that sodium has 3 shells. And that goes to mean that sodium belongs to period 3 of the periodic table. Sodium is in period 3 of the periodic table. Okay, so that's just the idea. All right, let us look at chlorine and see which period chlorine belongs to. Atomic number 17, and this is the electronic configuration. Okay, yeah. Now I'm going to ask you straight on. What is the highest principal quantum number here? And you'll agree with me, it is 3, is that not so? You see that in that 3p, 3p5. They also have it in 3s2. So the idea is that the highest principal quantum number here is 3. Therefore, we conclude that chlorine is in period 3 of the periodic table. How about you write the electronic configuration of calcium? Yeah, write the electronic configuration of calcium. Then tell me the period that calcium belongs to. Then go ahead, write the electronic configuration of scandium. Yeah, scandium. Tell me the period that scandium belongs to. Is that okay? All right, let's move on. I'd like us to look at this next one. Let's look at this next one. Good. Iron. Iron. What period does iron belong to? Now, if you look at the highest principal quantum number in this electronic configuration is 4, which is where you have that 4s2. And since the highest principal quantum number is 4, it simply means that iron belongs to period 4 of the periodic table. If maybe we are to use the circular notation of drawing atomic structure, are you getting? We are expected to maybe drop to like 4 shells, as the case might be. So you can see the relationship between electronic configuration of an element and the period that the element belongs to, which also goes further to explain the number of shells that the element has. I hope you're getting the point, right? Okay, now we are going to move further to the next item. We are going to look at the relationship between electronic configuration and the group of an element. Relationship between electronic configuration and the group. We have looked at the relationship between electronic configuration and period. What about electronic configuration and group? Now, I'd like you to get ready and put down this. We've defined what the group of an element actually is as the vertical arrangement, okay, that's the group rather of the periodic table. We have actually defined what the group of the periodic table is, which is the vertical arrangement, the column arrangement of the periodic table. Now, what is the significance of the group of an element? What is the significance of the group? How can you use the group, maybe the electronic configuration to determine the group of an element. So I would like you to put down this, please. Put down this. The group of an element tells us or determines the number of electrons that the element will have in its outermost shell. The group of an element determines the number of electrons that the element will have in what? Its outermost shell. Which simply means if I tell you the number of electrons in the outermost shell of an element, you have simply known the group of that element. You have known the group of that what? Element. Are you following, right? So you want to take note of that. Now, let us apply it to our electronic configuration. I would like us to look at this particular one showing, which is for iron. Iron, okay? Now, what is the period of iron in the periodic table? What is the period of iron in the periodic table? The group rather, not period. What is the group of iron in the periodic table? So you take a look at it, okay? If you take a look at it, you find out, you can find out actually the group that iron belongs to. Is that okay? You can find out the group that iron belongs to. All you have to do is to look at the valence shell. Look at the what? Valence shell. If you look at the valence shell, it can give you information about the group that iron belongs to. To give you information about the group that iron belongs to. You can see what I underlined there. You can see what I underlined there. Now you notice that I underlined 4s and 3d. I underlined 4s and 3d. Why did I actually underline 4s and 3d? Because we have to know what the valence shell, we have to know what the valence shell of iron is. Okay? Now, the subshells that I underlined there represent, the subshells I underlined there represent the valence shell of iron. They represent the valence shell of what? Iron. So if you look at the number of electrons in the two valence shell, you are going to get 2 and 6. If you add 2 and 6, you get 8. So it simply tells us that iron belongs to group 8 of the periodic table. But unfortunately, the group 8 we are talking about here, please, is not for the first 20 element. I'm sorry that I had to bring this up because there's something I just want to show you there. How to determine the valence shell of D block elements, okay? How to determine the valence shell, the outermost shell, the last shell. You get them using this formula. You get them using this formula. I think, let's see. All right. I don't think I have it here. I think I prepared that for next class anyway. Okay, I have it. It's here. Look at it. Observed trend of the form of valence shell of the D block element. So the outermost shell of D block element follows this format. NS2, where N there represents the principal quantum number, the highest principal quantum number in the electronic configuration. For example, in the case of iron, the highest principal quantum number is that 4. In the 4s2, that 4 there is the highest principal quantum number. You can see that. So if you want to get the outermost shell of D block element, it follows this format: NS2 bracket n minus 1, then d raised to any power, that is any number of electrons. That n there is the highest principal quantum number in the electronic configuration. So you see that of iron, the highest principal quantum number is 4. So that 4 will also be considered in the valence shell. Then after that, you will consider the last d that you have there. And how do you get it? Simply do n minus 1 to get the next principal quantum number that you will consider to be among the valence shells. Using iron as an example, as you can see displaying on the screen, the principal quantum number, the highest one there is 4. So that 4 will form the valence shell. Then if you do n-1, which will now be 4 minus 1, you will get 3d, because you have n-1d. Are you following, right? So 4 minus 1 will give us 3. That is 3d. Then that x there, okay, how many electrons does the d orbital carries? So coming to our ion, you have 3d6. So considering the highest principal quantum number, which is 4, and then checking for the d orbital, which will go as 4 minus 1, the two guys put together will help us to get the valence shell of that element. And once you know the valence shell of an element, all you now need to do to get the number of electrons is simply to add the number of electrons you have there. Just count them. In this case, it is 2 plus 6, giving you 8. So that is the reason why we can comfortably say that iron is in group 8 of the periodic table. Now let us consider this. Let's look at this one for sodium. Let's look at for sodium. For sodium, you notice that the highest principal quantum number there is 3. The highest principal quantum number there is 3. For S-block elements, I repeat, for S-block elements, if you want to know the valence shell, it is simply the highest principal quantum number. So the valence shell, the outermost shell, okay, or the ultimate shell, because these three words, they mean the same thing. The outermost shell of sodium is that principal quantum number 3. Okay? So, how many electrons do we have in that 3s there? Just 1 electron. And because it is 1 electron, it simply means that sodium is in group 1. So you see, we've been able to get the valence shell. Once you get the valence shell, which is the outermost shell of that element from the electronic configuration, then quickly check for the number of electrons you have there. That is in the case of S-block elements. You agree with me? We have explained that sodium is an S-block element. Now I'm going to show you the formula that it follows generally. For any element that is S-block element, as it is generally in the first 20 elements. Are you following, right? In the first 20 elements, take notes. That is why our part 2 class is going to be a very important class. In fact, it will not be live per se. Okay, it's going to be a pre-recorded video, so you can also follow up and see. I'll take my time to make analysis on the board. I hope you're following, right? So for the first 20 elements, if any element belongs to the S block, if you want to get the number of electrons, generally it goes with this formula that you have here. It goes with this. That is what usually happens. Okay? Yeah. Here is an S block element. So the valence shell will simply be NS, then that X there is the number of electrons that the S orbital carries. And X in that case will either be 1 or 2. So in the case of sodium here, the number of electrons in the outermost shell is 1, which we call the valence electron. Therefore, sodium belongs to group 1. So you see how we are using the electronic configuration to actually answer this question. Let us look at that of chlorine. That of chlorine, let's see the group that chlorine belongs to, looking at the electronic configuration. Now, this is the electronic configuration of chlorine. So what you have to do is ask yourself, what is the highest principal quantum number? Now, the highest principal quantum number in this electronic configuration is 3. And you can see it, we have 3s, we have 3p. So you must consider both of them. You must consider both of them. The last electron of this guy entered p orbital, as you can see that, which is in the 3p5. But we still have another principal quantum number 3, which goes with s. So the valence shell is these two guys, 3s and 3p. So all you have to do to know the number of electrons in that valence shell, in that outermost shell, you add their electrons. So in the 3s, we have 2 electrons there. In the 3p, we have 5 electrons. So add 2 and 5, you get 7. So chlorine belongs to group 7 of the periodic table. So I hope you are following what we are doing here. You see, the first thing we have to do if we want to know the group is to determine the valence shell, the outermost shell. Are you following? Once we know the outermost shell, all you now have to do is to check the number of electrons you have there. And how do we find out the outermost shell? Depending on the block of that element. I repeat, depending on the block of that element. And depending on the highest principal quantum number there. Like in the case of chlorine, you see we had to combine both the S and the P. Are you following, right? First of all, we found out that the last element or the last electron entered p orbital here, which is 3p5. So at least we are going to consider somehow, some way that's p orbital. Then we notice that the highest principal quantum number is 3. The highest principal quantum number is what? 3. Therefore, we needed to consider the 3s also. So adding the electrons together, you get 7, which gives us group 7. That chlorine belongs to group 7 of the periodic table. Okay, now let us look at this one that is a bit funny. For radon, atomic number 86. Let's look at the electronic configuration, and then we get to know the valence shell as well as the number of electrons in that. So this is the electronic configuration of radon. You notice that the last electron entered p orbital. The last electron entered p orbital, which is that 6p6 there. But hey, there is another 6 there, as you can see. There is another 6 there, which is 6s2. I underlined it. Which means to get the valence shell, the outermost shell of radon, we'll consider the 6x, the 6s there, we'll consider the 6p. But you notice again that I underlined 5d. I underlined that 5d10 there. Why did I underline that 5d? That is why it's also important for you to know that by the time you start going a bit higher, are you getting me right? Into all these transition metals, you move on into the lanthanide and actinide, which are inner transition metals. Are you following right? The lanthanide and the actinide, there are certain rules that guide them. Like I said, for this actinide and lanthanide, I would explain their concepts more in our next class. Okay, but let us look at this. You notice that I still apply the n-1 rule here. Yes, I apply the n-1 rule. That thing usually happens in the case of D block element, okay, transition metals to be specific, as well as the lanthanide and the actinide. Usually we apply that n-1 rule. So now that we know that the highest principal quantum number in the electronic configuration of radon is 6, we will pick that. So n is equal to 6 for this guy. Then we will check for n-1, which is 6 minus 1. 6 minus 1 gave us 5. So I underlined that 5. But there is a problem here. I underlined this 5d, but I did not underline 5p. I did not underline 5s. So what is the reason for that? Now I'll just highlight one thing. Then in our next class, I will give further explanation. I don't need to underline 5s and 5p here because their energy level is far lower than that of 5d. I repeat, their energy level, if you apply of Bohr's principle, look at the arrangement now. You notice that after 5s, you will cross 4d, you have 5p. Now, after this 5s and 5p, you now start climbing up to other higher energy level. You go to 6s, you go to 4f, then 5d. You notice that the 5d is far ahead of 5s and 5p. So that is one of the reasons why, even though I used n-1, which brought in 5d among the valence shares of this guy, don't go and confuse yourself picking 5s and 5p. 5s and 5p are at a far lower energy level compared to 5d. So if you're applying your n-1, please take note that that n-1, the subshell it is going to take will be the d, not the p, and not the s, even though you are seeing 5s and 5p here. So this is a brief explanation to this. But like I said, in next class where I would take of the periodic table, are you following? Where we have the S block, the P block, the D block, and the F block. We talk about the concept of metals, non-metals. We talk about transition metals. We talk about the lanthanide and actinide. I'll explain further. So until then, just take note of what I've told you. So here, the valence shell, the outermost shell will include those ones with the highest principal quantum number 6, and then applying n-1 d rule, we're going to get 5d because we have 6 minus 1, which will give us 5. 5d would now come in to join the valence shell. So if you add up the number of electrons we have there, which are in the 6s, we have 2 electrons. In the 5d, we have 10 electrons, making it 12. In the 6p, we have 6 electrons, making it 18. You would see that radon here is in group 18. Group 18. Now let me ask you, we have talked about the period. Which period does radon belong to? Which period does radon belong to? You can drop your answer in the comment section. Okay? You can drop your answer in the comment section. So this is good. And I hope you understand what I've actually taught so far. If you have any question, make use of the comment section, drop your question there, and I will respond. The last thing we want to consider is the concept of family / names of the groups of the periodic table. All right? Families or names of the groups of the periodic table. I am going to focus, of course, on that of the first 20 elements, okay? That of the first 20 elements. So I'm going to bring out the periodic table. So we look at the groups. We have group 1, 2, 3, 4, 5, 6, 7, and 8 or 0. So group 1, what is the name of that group? So that the elements are in that group, how do we refer to them generally? You can put that down. Group 1 elements are called alkali metals. Alkali metals. In part 3 of periodic table, we'll talk about why they are called that, okay? I want to believe you've heard about alkalis before from the study of bases. Yeah, soluble bases are called alkali. So there is something, the group 1 element, they are bases, they are soluble. So that's why, that's where that name or something came from. So we'll talk about them when we explain these groups and their names, why they bear that name. Group 2 is called alkali earth metal. Alkali earth metal. Group 3 is called boron family. Group 4, carbon family. Group 5, nitrogen family. Group 6, oxygen family. Group 7, we refer to them as halogens. Group 7, halogens. Group 8, refer to them as the noble gases. The noble gases or the rare gases. So these are the names of the 8 groups in our first 20 elements. Although in the modern periodic table of 18 groups, we don't have any classified name for them or so. We usually focus on these ones that I've mentioned in this lesson. All right, guys, this is how we come to the end of this class, and I hope you learned something wonderful from this lesson. These are the things we've covered. We talked about what periodicity is all about, and we say it is simply the repetition of similar properties, okay, of properties in the periodic table. We talked about the modern periodic law, that this was proposed by Henry Moseley, okay, who modified the Mendeleev's table. Now we went ahead to also talk about the groups and period, that groups are the vertical arrangement, and they give us information about the number of electrons in the outermost shell of an element. Now we'll talk about period, the horizontal arrangement, the rows. And we'll say that the period gives us information about the number of shells that an element has. Point number 3, we learned about the electronic configuration and the block of an element, where I explained that we identify the block of an element from the subshell that the last electron entered. So if the last electron entered the S subshell, it means that the element is an S block element. If it enters P subshell, that element would be a P block element. If the last electron enters the D subshell, that element will be D block element. And if it enters the F subshell, that element will be what? It will belong to the F block. Then we also use the knowledge of electronic configuration to determine, to find out the group that the element belongs to and the period that the element belongs to. I started explaining with that of period. From the electronic configuration, if you want to know the period of an element, it is simply the highest principal quantum number, which is the numbers attached to all those subshells. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p in that order. So the highest number, principal quantum number, that is what will tell you the period of an element. And what about the group? We say that the group of an element is or are obtained. I'm going to say it is obtained from, the number of electrons that the element has in its outermost shell. The group of an element is or are simply the number of elements in the outermost shell of that element. The number of electrons, I repeat that, the group of an element is or are the number of electrons in the outermost shell of that element. So if I write the electronic configuration of an element and I want you to tell me the group of that element, what you have to do is first find out the valence shell. Valence shell is the same as outermost shell, is the same as ultimate shell. Find that out. And how do you get it? Simply, you can use the highest principal quantum number. There are cases you can also apply the n-1 rule. That happens from the transition metals and the lanthanide and actinide. You have something like that where you apply n-1, n-2 rule and other things. So from there, just check the number of electrons that the outermost shell has. If you know the number of electrons the outermost shell has, that is simply the group of that element. And then we concluded with the names of the groups of the periodic table. So, with this, you can be able to answer any question that comes from this aspect of periodic table. If you're yet to subscribe to this channel, please hit the subscription button, turn on the notification bell so that anytime I upload any new content or have a similar class as this, you will be personally notified. And don't forget, like I always say, you can always become a channel member on the GMAETS 41's platform, where you get access to a lot of learning material. You can also join our tutorial physically in Unizik campus if you are a Unizik student in 100 level. I hope to see you in our next class. Until then, do take good care of yourself and remember to take your studies seriously. Is that okay? Take your studies seriously. Remember that you will always be tried by your examiner. Therefore, you want to always study hard. If you have any question, please do not hesitate. Feel free to drop the question in the comment section and I'll be there to respond. Do have a wonderful day and see you in my next video lesson.